Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. In the previous video, we saw that measurement error in x pulls the estimated slope towards zero. Now, let's prove that mathematically and derive exactly how much shrinkage occurs. Now, the derivation has 4 moves, so follow each one carefully, and while the logic is tight, the algebra is quite simple, so you should have an easy time following through as well. Let's look through the setup first. So the true model that we have is y being equal to beta 0 plus beta 1 x star plus an error term u. X is the true regressor, but remember we observe x, which is x star plus some error term v here. The assumptions that we are going to hold, because we are under the idea that we have classical measurement error. So the assumptions are that on expectation v is equal to 0, the covariance between v and x star is equal to 0, so error independence of the true value, and the covariance between v and u, that's also 0, so error is independent of the structural error. These 3 assumptions define classical measurement error, and all 3 are needed for the derivation that follows. Now, the second assumption that we have written in here is the key classical assumption, and we've seen this everywhere even when we did omitted variable bias, so we're going to keep using it here as well. And what it says is that measurement error is not related to the true value of x. So rich people don't systematically misreport more than poor people, and so on. If we ignore the intercept, okay, OLS estimators, so we're going to have beta 1 hat being equal to the covariance between x and y divided by the variance of x. That's the typical formula that we know for the OLS estimator, and this is exactly the same starting point we've used throughout this series. Now we'll substitute in the measurement error structure and see what happens. So for the first one, we would have the covariance of x and y, but remember x is x star plus v, so we're looking at that with covariance with y. And using linearity of covariance, we've shown the properties of all of the variance, covariance, and expectation operators in previous videos in this series, so make sure you check them out if you have forgotten how to use the linearity property of covariance. But ultimately, this is equal to the covariance of x star with y plus the covariance of v with y, which we know is equal to 0, okay? If you want, try to think also for a moment, what exactly is this covariance of v and y? In a sense, what you're saying in here is that the error term, the measurement error v in here is correlated or not with your y variable, but we already know it's uncorrelated with the error term, uncorrelated with your x star, like as we have set it out, so clearly it should follow that. The further step is that, well, it shouldn't also be correlated with the y, because otherwise then we run into other endogeneity issues. Now let's substitute the true model, okay? If we had the entire true model, and like we can show where this is coming from, okay? So if we have covariance of v and y, we would have, this is the same as covariance of v with y being beta 0 plus beta 1 x star plus the u. Again, using the linearity of the covariance, this would have been covariance of v with beta 0 plus beta 1 covariance of v with x star plus covariance of v and u. And covariance between a variable and a constant, that's equal to 0. We already set out in our assumptions that there is no covariance between the v and the x star, so that's also 0. And ultimately, the third assumption was that the covariance between v and u was 0, so that's also 0. Okay. So what that means is that ultimately we can write the covariance of x and y being equal to simply the covariance of x star and y, while we keep the variance of x in here for now. Okay. So we did the expansion of the denominator. Let's now do as a second step the expansion of the denominator. So variance of x. What is the variance of x? Well, we know that x is x star plus the v. We're going to use the variance rules, which means that this is equal to the variance of x star plus the variance of v. And normally we would also have two covariance of x star and v, but we already know that this is equal to 0, okay? So right now we're only left with variance of x being equal to variance of x star plus variance of v, okay? And this in here is also the key difference between the measurement error case in the y. The denominator, we can see it's clearly inflated because it contains both true variation and the measurement noise. The numerator was, in a sense, unaffected. The denominator now has grown, so the ratio to the OLS estimate must shrink. So let's substitute it back in here, or maybe it might be easier if we do this. So we have covariance of x star and y in the numerator, and then here we have variance of x star plus variance of v in the denominator. So again, numerator unaffected, but now this has increased. It's been inflated because it's got the true variation and the measurement error variation all together, so the measurement noise. So the ratio overall, ratio must shrink. Okay. Now let's think about this more carefully. Like, we can actually rewrite this expression slightly differently. So if we use the true model to actually evaluate the covariance of x star and y, that would literally be, so if we have covariance of x star and y, we would have that this is the covariance of x star with beta 0 plus beta 1 x star plus u, which would be covariance of beta 0 with x star, then plus beta 1, covariance of x star with x star, and ultimately covariance of x star with the u. We already now know this is 0, this is also 0, and covariance of x star with x star, that's just the variance. So this is beta 1 variance of x star. So ultimately, it turns out our beta 1 hat can be further written as beta 1 variance of x star divided by variance of x star plus the variance of v. Okay? And another way to sort of write this so we don't have to write variance all the time, it is like beta 1, the variance we can say sigma square of x star in here divided by sigma square of x star plus the sigma square of v. Okay? So the true beta, what this expression is telling us is that the true beta 1, okay, is multiplied by this fraction that is always strictly between 0 and 1. Because look, the numerator is smaller than the denominator, okay? And that fraction this entire fraction that you see in here, this is your attenuation factor. Okay? It tells us exactly how much the slope shrinks. Okay? So once again, let's very quickly go through how we got to this place. So we started from the beta 1 definition that we had, covariance xy over covariance of x. By further working the covariance of the x and y by substituting first the x and then by substituting the y, we managed to express that ultimately as simply beta 1 variance of x star. And then the denominator, by substituting the x with the expression that we have, we found out that it's ultimately the variance of x star plus the variance of v. This entire expression, it's telling us that our estimated beta 1 is the true beta times this fraction in here, this ratio, which ultimately is the attenuation factor and telling us by how much it really shrinks. Okay, I hope this was helpful, and now you have a better grasp of what the mathematics behind proving that attenuation factor is. Stay tuned, because in the next video, we're going to talk a little bit more in detail about the attenuation factor and attenuation bias and also extreme cases. So stay tuned, and I'll see you next video.